Right, now let me say like this. So when it comes to the mapping concept, first of all, we need to identify there are two types of memory. First one is virtual memory, and the second one is the physical memory. So virtual memory, the concept we have already studied. So today I'm going to explain you the mapping concept. So when it comes to virtual memory, we'll imagine there this side we have the virtual memory, okay, and here we have our physical memory, which is basically referred to as the RAM, right? So in this virtual memory, in our virtual memory, right, and this is our physical memory, basically the RAM, physical memory. And also we can divide, we can categorize, we can divide the virtual memory into two. The first one is, right, first part is the page number, and the second part is basically called the offset or displacement. First part is called the page number, and this part is called as the page size. We can call the page size also, or either we can also call as displacement. Displacement is also another word, or also we can call offset. All these three refer to the same meaning, right? Page size, displacement, or offset. And when it comes to our physical memory, it also can be categorized into two. First one is the frame number, and next one is the frame size. First one is the frame number, and the frame size. So we have the frame number, and in the next part we have the frame size, or also we can call also displacement or offset. That is also fine, right? Displacement or offset. So now displacement or offset, where we can call that, okay. So frame number, this one is our frame number, and this part we can call as frame size. Now we'll imagine our virtual memory address space, right? We'll imagine we are using 4 bits for our virtual memory, right? We are using 4 bits for our virtual memory. And also we'll imagine for the physical memory also we are using 4 bits. For the physical memory also we are using 4 bits, right? For virtual memory also 4 bits, and also for the physical memory 4 bits. And also we'll say the page size. The page size is, for the page size we are allocating 2 bits. For the page size we are allocating 2 bits. So if we are allocating 2 bits for the page size, obviously it must be clear for you, right? So here 2 bits. So total, right? The total we have told the total is 4 bits. The total is 4 bits. So for the page size, if we are allocating 2 bits, for the page number, the remaining 4 minus 2 is 2. So the remaining 2 bits will be allocated to the page number. And also in the last class, I have already informed you guys that if the page size is 2 bits, I have already told that the page size is equal to the frame size. The page size is equal to the frame size. So if the page size is 2 bits, so obviously the frame size is also will be 2 bits. There is no doubt on that, because page size is equal to the frame size. Page size is equal to the frame size. So here in total we are allocating 4 bits for our physical memory. So if 2 bits are allocated for the frame size, the remaining 2, that means 4 minus 2, the remaining 2 bits will be allocated to the frame number. The remaining 2 bits will be allocated to the frame number. Now it is okay, we are done. Now all these informations are given, right? Now we will see how many pages will be created and how many addresses will be created. Now here we are having, okay, now here in this case we are having 2 bits for the page number, 2 bits for the page number. So if we are having 2 bits for the page number, we can create 4 pages, because my dear 2 to the power 2 is 4. So we can create 4 pages. So if there are 2 bits allocated for the page number, 4 pages will be created. 4 pages will be created in our virtual memory. So let me draw the first page. Let me draw the first page. Okay. First page, second, third, fourth, like that. 4 pages will be created. So this is our first page, right? First page. And this is our second page, right? Second page. And this is our third page. Third page. Why 4 pages are created means because we are allocating 2 bits. We are allocating 2 bits for the page number. As because we are allocating 2 bits for the page number, 2 to the power 2 is 4. 2 to the power 2 is 4. Therefore, 4 pages will be created. So this is going to be page 0. This is going to be page 0. This is going to be page 0. Right? And this is going to be page 1. This is going to be page 1. Page 1. Page 1. And this is going to be page 2. This is going to be page 2. And this one is page 3. So if you take the count, there will be 4 pages. If you take the count, there will be 4 pages. So now it is clear 4 pages will be created. Right, fine. Now we know there is a thing called page size now. So this side we are having page size or displacement. Or also we can call offset. All are similar meanings. So here for the page size, we are allocating 2 bits, as because we are allocating 2 bits for the page size in the logic gates lesson. Also we have understood the logic. So 2, if there are 2 bits, 2 to the power 2 is 4. So 4 combinations we can create. So if in the logic gate lesson I have explained, if there are 2 inputs, right? So there will be 4 input combinations. 4 combinations can be created because 2 to the power 2 is 4. Here also the same logic, as because the 2 bits are allocated for the page size, you can create 4, right? 4 addresses in each page. 4 addresses in each page. Okay. So here, for page size will be 4, because 2 to the power 2 is 4. Right? 2 to the power 2 is 4. So in one page is 4 addresses will be created. So if you take the total pages, so we have altogether 4 pages. So in one pages 4 addresses are created, means 4 into 4 is 16. Altogether 16 addresses will be created. So in one page we are having 4. That means for the page size we are allocating 2 bits. So 2 to the power 2 is 4. That means in one page 4 addresses will be created. Right? So if there are 4 pages, so 4 into 4 is 16. Where 16 addresses will be created. 16 addresses will be created. So this is first one, right? In this case, right? And here also 4 addresses will be created, right? 4 addresses will be created. 4 addresses will be created. Okay. Here also the same. 4 addresses will be created. Wait for my explanation, so it will be more crystal clear if once I done with this, right? So wait, first of all I will explain it. So we are done with this. Now we know, so first one is what 2 bits we are allocating. We are allocating 2 bits now. So when we are allocating 2 bits here, as because we are allocating 2 bits here, we know that page number, and this is page number, so 4 pages will be created. Now this is page 0. So how to write 0 in binary with 2 bits? We know that very simple. How to write 2 bits in binary? That means 0 0 0 0. So our page zeros page number will be 0 0, right? The second one also will be 0 0 only, 0 0 only. Third one also 0 0. Fourth one also 0 0. Because all these belongs to which one? All these 4 bits, right? All these 4, that means all, right? These 2 bits, all the first 2 bits are representing the page number, right? Because if you see the virtual memory, 2 bits, first 2 bits are allocated for the page number. So that's what this is 0 page. That's why we are making all the first 2 bits as 0 for everything. So 0 0 0 0 0 0, and this is page 1. No, so how to write binary 1? That means how to write decimal 1 in binary using 2 bits is 0 1. That is using 0 1. That is using 0 1. Okay, 0 1. Right, using 2 bits. Okay, so as because using 2 bits, it's going to be 0 1. 4 bits means your answer is correct. So here it's going to be 0 1. Next one also 0 1 0 1 0 1. Right, that's okay, done. Now here in page 2, we are going to write binary, right? Decimal 2 in binary. So how to do that? So that must be 1 0. That must be 1 0 1 0 1 0 1 0. Right? So that is done. So this is referring to the page number 2. So how to write page 3? That means how to write 3. How to write 3 in binary? Yes, fine, good. Your answer is correct. So that is 1 1. That is 1 1 1 1 1 1 1 1. So these things are nothing for you because we have done enough questions in these things, right? So this is very easy. This is very easy, right? So right now we are done with the first 2 bits. We are done with the first 2 bits. First 2 bits we are done, but still there are some other bits we need to do. That means the remaining 2 bits we must do. We'll do that. Don't worry. So here 1 0 1 0 1 0 1 0. Right. Now here it's going to be 1 1 1 1 1 1 1 1. Right. Now we are done with the first 2 bits. We are done with the first 2 bits. That means first 2 bits are referring to the page number. First 2 bits are referring to the page number. So we are done with the page number. But we have the remaining 2 bits. The remaining 2 bits are for the page size. The remaining 2 bits are for the page size. So page size 2 bits are there means I have already told you the logic. The logic is where you must for an example, in the logic gates lesson, if there are 2 inputs, 4 combinations can be created. So those are going to be 0 0 0 1 1 0 and 1 1. So we are going to write that here. That's all. That's all. Right. So the remaining 2 is going to be 0 0 as the first one, 0 1 as the next one, 1 0 as the next one, and 1 1 at the last. So this is our virtual address. This is our logical address. Logical address. So this is what we call as logical address, not more than this. So this what you see 0 0 0 0 is the first logical address. 0 0 0 1 is the second logical address. 0 0 1 0 is the third logical address, and 0 0 1 1 is the fourth logical address. Now this is what we call as logical address. So in the virtual memory, we will be getting logical addresses. The virtual memory, we will be getting logical addresses. Logical addresses. So now in the second one also the same thing only. Why we call second one also the same thing? Because here also we are going to say 0 0 only, because same no 0 1 1 0 1 1, right? 1 1. Those things are not going to change. And here we are going to say, here we are going to say also 0 0 0 1 1 0 and 1 1, because the remaining page size displacement is 2 bits now. Here also 0 0 0 1 1 0 and 1 1. So that is done. So page 3 also now done. So it is very clear for us. So we are done with that. So if you note here, there are 16 pages, 16 addresses will be created. So this is our first address, this is our second address, right? This is our third address, this is our third address, this is our fourth address. So like that, this is our fifth address, sixth. That's what happening. So here also for the frame number, we are having 2 bits. As because we are having 2 bits for the frame number. So what is happening here also, 2 to the power 2 is 4. 4 frames will be created. 4 frames will be created. So this is our first frame, right? This is our second frame, and this is our third frame, and this is our fourth frame. So those things will be created as it is. So and also when it comes to the this one, so I will come to the frame. So this is frame 0, this is frame 0, right? So frame 0 here, let me say frame 0. This is frame 0, frame 0. And here it's going to be, this is our frame 1, this is our frame 1. So 4 frames also will be created because the bits allocated for the frame number is 2. So 2 to the power 2 is 4 created. Here what happened? 16 logical addresses were created, right? Here 16 logical addresses were created, and here 16 physical addresses will be created. Here 16 physical addresses will be created, right? 16 physical addresses will be created. Physical addresses, right? Physical addresses will be created. Will be created. So that's the logic. That's the logic. So here let me come. So this is first one. This is our second one, and this is our third one, and finally fourth one. So here also first one. This one the second one, and this one the third one, and finally the fourth one. First one, right? Second one, and the last one, the third one, and finally the fourth one. Here also same in the frame 4 also it's the same thing. There is no any difference because here also the page frame size is 2 bits, no? So when 2 to the power 2 is 4. 2 to the power 2 is 4. So it will be created as it is, right? Now we'll come to the frame 0. So frame 0 means it is sorry, frame number, no? So this is frame 0. So how to write 0 in binary? 0 0 only. So 0 0 0 0. So that is okay. Now here this is frame 1. This is frame 1. So frame 1 means how to write binary. That means decimal 1 in binary. That is using 2 bits. 0 1 0 1 0 1 0 1. Yes, good, good. 0 1. Here 1 0. Why 1 0? How to write right? So this is first one or 0 1. This is 1 0 because this is the second one. This is the second one. So frame 2, right? Frame 2, and this must be the frame 3. This must be the frame 3, right? Frame 3, right? Now done. Still not done. Wait. Right. So how to write 3 in binary? How to write 3 in binary? That is, yes, come on, say. That is 1 1 1 1, right? 1 1 1 1. Right. Yes, good. Right. Now I will come to that. Yes, okay. Now right, okay, listen carefully. I will explain that. Now here we are done with the first 2 bits, but if you look at here, my dear, if you look at my dear, now we are done with only the first 2 bits. That is only the frame number. That is only the frame number. But in our if you take our physical memory, physical address, our physical address must consist of, my dear, 4 bits, but we have done with only 2 bits. So remaining 2 bits, what? Frame size, frame size. So if there are 2 bits, 4 combinations will be created. First one is 0 0. After that 0 1, writing 0 1 2 3 in binary, guys. Writing the decimal 0 1 2 3 in binary. That's all. Okay. So let me come here and put 0 1 here. Sorry, first one is 0 0, then 0 1, then 1 0, then 1 1. Okay, now we are done with that. Now here also we are having 0 0 0 1 1 0 and 1 1. And here also 0 0 0 1 1 0 and 1 1. Okay, no? So here also 0 0 0 1 1 0 and 1 1. Right, done. Now here, so I will give you a conceptual visualization here, right? So in the virtual memory, we are having 4 bits. So 2 bits for the page number and the remaining 2 bits for the page size. So when there are 2 bits allocated for the page number, 2 to the power 2 is 4, where 4 pages will be created. And this page size refers how many addresses will be created in each page. So 2 to the power 2, 4, no, my dear. So 4 logical addresses will be created in each page. So in each page, 4 logical addresses created means when there are 4 pages, 16 addresses will be created. So this is our first one, first address. This is our second address. This is our third address, and this is our fourth address. This is our fifth address. This is our sixth address, seventh address, and eighth address. So this is our ninth address, 10th address, 11th address, 12th address. This is our 13th address, 14th address, 15th address, and 16th address. So here also the same idea. The difference is this is physical address, this is logical address. Okay, now? All right. Now there is a guy called page table. This is the key. What is page table, my dear? Page table means that table is responsible for mapping which page number should be mapped with which frame number. That means if we take page 0, okay, page 0 must be mapped with which frame number? Is it frame number 0? Is it frame number 1? Or is it frame number 2? Or is it frame number 3? That detail is stored in our home, our page table. So I am going to explain the important thing here, that is the page table. So page table is coming here, right? Page table is coming. So this is the page table. This is our page table. So our page table consists of which page number will be mapped to which frame number. So that is our what? That is our page table's responsibility, right? So, right? I will explain. Don't worry, right? So we are here and here, right? Okay, fine. So, and let me have 2 columns, right? So, and here we are having the page number. Here we are having the page number, and the other, on the other side we are having the frame number. Then only we can say which, we know that which page number is mapped with which one. So here I will say page 0 is going to be mapped with page 2, right? And page 1 is going to be mapped with frame 1, and page 2 is going to be mapped with frame 0, and page 3 my dear, is going to be mapped with frame 3. Now listen to the logic. Now I will say this is the I am having A. So if this is A, I am going to search. Okay, now this is in the virtual memory. So our operating system is responsible for mapping our page, now a page table. We should see the page table, right? Our operating system must see, right? Okay, here A, no. So this A, that means A is in which table? Sorry, in which page? A is in which page? A is in page 0. Now come to the which one? Come to the page table, my dear. Come to the page table. So page number is 0. Okay, what is the frame number it will be mapped? What is the frame number it will be mapped? Frame number 2. Frame number 2 means which one, my dear? This one. It will be mapped to frame 2, right? That means, right, from virtual memory we should transform the data. That means from virtual memory data to which physical memory address it will be mapped. That is what mapping is. So we know that that will be mapped to frame 2, but we don't know which location. That means which address, this address or this address or this address or this address. Okay, that's what we have. What? Displacement, my dear. So what is the displacement of this? What is the displacement of this? 0, 1. 0, 1. How to find the displacement, my dear? I told you just now before. Page size. Page size or displacement is the 2 bits. The ending 2 bits are there, no? That is the displacement. So what is the displacement of A? 0, 1. So come to the frame 2 and search for 0, 1. This one, no. So this address, my dear, will be mapped to this address. That is the logic. This is what mapping is. Right? Now I will explain another example also to be more clear on this. So it will be crystal clear for you. I will say there is B, a data called B here. So this B is in the virtual memory, my dear. It is in the virtual memory. but it must be transferred to the physical memory. Why? Our CPU can directly access only the random access memory, my dear. Our CPU can only access the random access memory, but now this B is in the virtual memory, so our CPU can't directly access the secondary memory. So first of all, it must be transferred to the physical address. That means the random access memory. Therefore, our operating system should decide to which address this B is going to be transferred. Now we know the logical address is 1010. That means page number is 2, my dear. Page number is 2. So come to the page table. That's why our operating system has a page table to identify which page will be mapped to which frame. So we are having page number 2 no here, my dear, 2. So it will be mapped to which frame? Page number 2 will be mapped to which frame? 0. Okay, 0 frame. 0 frame is which one, my dear? This frame will be mapped to this frame. Okay, fine. In this frame 0, we have 4 addresses. In these 4 addresses, to which one it will be mapped? Do we know that? Yes, you can find it out. Using what? Using the displacement or offset. So what is the displacement here? To come to this one, the ending 2 bits, right? The final 2 bits of our logical address, the final 2 bits of our logical address is the displacement. That means the displacement of B is what? Displacement of B. That means the remaining final 2 bits are what? 1 and 0. So now come to the frame 0, where you see 1 and 0. You see 1 and 0 here. That means, my dear, this logical address will be mapped to which physical address? To this physical address. This is what mapping is. This is what mapping is. Not more than that. I will say you another example also to be thorough on this, right? So we'll say there is a data here, right? We'll say E is here. Now E is in the page number 3. So this E cannot be accessed by the CPU. Why? This data is currently in the virtual memory, right? Right. So it must be transferred to the random access memory or the physical. That means a RAM. Then only our CPU can access it. So the page table is responsible for mapping our operating system. So what is the page number? Page number is 3. Page number is 3. So come to the page table. So that's why we have the page table. So page number 3. So what is the frame number it will be mapped to? Come on, say me. Page number 3. What is the frame number it will be mapped to? 3. Okay, where do we find frame 3? Frame 3 is here. We are sure it will be mapped to this frame 3. But we don't know where to which address will be it mapped, because we are having 4 addresses now. So here also you can find it out easily. How to find it out easily? Come on, the remaining 2 bits are for the displacement. The remaining 2 bits, the final 2 bits are for the displacement. So E is in the which displacement? 0, 1 displacement. So where do you find 0, 1 in the frame 3? Here. Then what's the logic? This logical address will be mapped to which physical address? This physical address, right? So this is, I think, now very clear for you. I think now this is very clear for you, right? So now Madhushan, right, wait, okay,